Hi, and welcome to topic B.2 the Greenhouse Effect. And this topic is something that we can all relate to a little bit easier because we're living it. We're living in the greenhouse effect. And it starts to take together ideas of temperature and black body radiation and put it into real world examples. In the last section, we've been assuming black body emitters. And I guess it's good to think of a star as a black body emitter, but now I'd like us to think about the Earth. And the Earth, what kind of emitter is that? What kind of absorber is the Earth? Is it a black body? Does it re-emit all the energy that it absorbs? Or are there barriers in the way for that happening? And to do that, we need to think about albedo and emissivity. We'll start with a little bit of actual examiner feedback here. The examiners have said that the statement of meaning of albedo as a ratio were rare. Learning of correct definitions is key. So we've got to learn the correct definitions of albedo and emissivity. Intensity is the power per unit area received by any object. So if we consider the intensity of the sun's rays on Earth, it would be the amount of energy received per second per metre squared on the Earth's surface. The albedo is the ratio of reflected to incident radiation. The Earth's albedo varies daily, and we will talk about that in a lot more detail on the next slide. The ratio of reflected to incident radiation. So if we have some radiation from the sun towards the Earth, some of it's reflected and some of it is absorbed. And the albedo looks at how much is reflected compared to how much is incident on it. Emissivity, let's look at that. Emissivity. The Earth and its atmosphere is not a perfect black body. So previously the equations we've looked at have assumed a perfect black body. The emissivity is the ratio between the power radiated by an object and the power radiated by a black body at the same temperature. So it's really an idea of how good a black body an object is. If it's a perfect emitter, it's a perfect black body, and the emissivity would be 1. If it absorbs loads of radiation, but doesn't re-emit anything, then its emissivity would be 0. And the Earth falls somewhere in between. Again, we'll discuss that later on. Let's look at intensity just now. So intensity is the power per unit area received. The intensity of solar radiation at the top of the Earth's atmosphere is called the solar constant. So if you imagine the sun radiating out lots and lots of energy, some of that will be received above the Earth's atmosphere before the Earth's atmosphere has had a chance to make any difference to the power. And the amount of energy per metre squared per second received by the sun is known as the solar constant. And that solar constant is 1,400 watts per metre squared. So every metre squared above the Earth's atmosphere receives 1,400 joules per second of energy from the sun. And we call that our solar constant. The albedo is known as the ratio of reflected to incident radiation. And it's a dimensionless number, it has to be less than 1. Unless all radiation is reflected, in which case the number would be 1. You can imagine that snow reflects quite a lot of radiation, so snow has a high albedo. In fact, 85% of the radiation incident on snow is reflected, so it has a high albedo. Charcoal has a very low albedo. It doesn't reflect very much at all. It has an albedo of 0.04. The average global albedo of the whole Earth is 0.3, although this does vary every day and at what point you're looking at on the Earth. That's why we call it the average global albedo. The albedo depends on the time of year. If there are lots of clouds in the atmosphere, in the sky, then the albedo changes. The latitude, if you're looking at the poles of the Earth, there are lots of snow and ice on the poles. The poles, therefore, tend to have a higher albedo. Desert land has an average albedo of between 0.3 and 0.4. And forests have a very low albedo, as do water and oceans, of 0.1. Only 10% of radiation on a forest or a water would be reflected back. 90% of that would be absorbed. Depending on where you look on the Earth and what time of the year it is, the albedo will change. So head to your revision note template, write down the definitions for albedo, intensity and emissivity. You'll also want to go to the extra notes section and write down some notes about the albedo of the Earth. Finally, I would write down the equation for intensity. Now we're moving on to B2.4 and 2.5, looking at the solar constant. I've previously said that the amount of power received per metre squared above the atmosphere of the Earth is 1,400 watts per metre squared, and that is known as the solar constant. The amount of light received by our whole spherical planet is exactly the same as the amount that would be blocked by a flat disk with the same diameter. So if you imagine the Earth all squished into one circle in a two-dimensional capacity, that's how much energy is received by the Earth. Therefore, our target area is a quarter of the total surface area, and the power per square metre received on Earth is a quarter of the solar constant. Therefore, the intensity on Earth is 350 watts per metre squared. I'm going to take you to a little diagram here. Actually, it's not a little diagram, it's a very big diagram. The Sun, our solar constant above the Earth, is 1,400 watts per metre squared. The target area of the Earth is equivalent to 1/4 of that. So above the atmosphere, our incoming solar radiation is a quarter of 1,400, which is around about 350 watts per metre squared. This does change. It's not an official constant. Like the solar constant I've just told you is 1,400 watts per metre squared. It's not like the constant of light, which is 3 times 10 to the 8 metres per second. And it's not like Newton's gravitational constant. It does vary, not quite a lot. It varies by 0.2% over the years and over depending on what's happening in the sun. But generally it's 1,400. You divide it by 4 to calculate what the intensity above the Earth's atmosphere is, and we get to 343 or 350 watts per metre squared. The Earth's average albedo is 0.3. That means 30% of this 350 watts per metre squared is reflected away. Therefore, 70% of this radiation is allowed through. So through the Earth's atmosphere, we receive 70% of 350, which is 245. So the net incoming solar radiation through the greenhouse and through the atmosphere is around about 240 watts per metre squared. And that is due to the Earth's albedo of being around 0.3. It's now a good idea to consider emissivity. Emissivity is the ratio between the power radiated by an object and the power radiated by a black body at the same temperature. The Earth will absorb the solar radiation. However, it's not a perfect black body and it will not radiate all of the energy it's absorbed. If we go back to the beginning of this tutorial and we looked at the Stefan-Boltzmann law, we said that a perfect black body will radiate energy given to this equation. And I've brought it back down to this slide here. If the body is a perfect black body, it will radiate that amount of energy. But for an object that is not a black body, the emissivity must be taken into account. Our Earth is not a perfect black body. It will radiate energy because it has a temperature, but it won't radiate all the energy that has been incident upon it. So we have to add the emissivity to the Stefan-Boltzmann law when we're looking at objects that are not perfect black bodies. Let's go right back to the start. Most energy received by the Earth from the sun is visible. It's visible light. A little bit of it is infrared, which keeps us warm, and some of it is UV radiation, which gives us a suntan and sunburn. 30% of that is radiated back into the atmosphere because of the albedo. 70% is received at the Earth's surface and it warms it up. The Earth behaves as an imperfect black body and re-radiates some of that energy. The type of energy that it re-radiates depends on the temperature of the Earth. And the temperature of the Earth is 288 Kelvin. That's a very, very low temperature, which means it will radiate a higher wavelength of radiation depending on Wien's law. So even though the Earth has received lots of visible light and visible radiation and high energy radiation, it will re-radiate electromagnetic radiation within the infrared wavelengths. Let me repeat that. The Earth will receive visible light, but it will re-radiate infrared radiation, which is heat. The Earth will re-radiate heat. And this is where the greenhouse effect comes into play. Let's head to your revision note template. First of all, in the common definition section, you'd write down the definition of a solar constant. Go to the extra notes section and write down why the effective instant power on the Earth's surface is S/4. And go to the common diagrams section and draw an example energy balance diagram of the Earth's atmosphere. You'll notice that we started talking about the Stefan-Boltzmann law, which links into the previous topic. And you should now see problems that are starting to link topics. For example, you will see questions about Stefan-Boltzmann law in greenhouse effect questions. We're going to start linking things together. Talking about linking topics, let's consider the Earth as a black body and see how that affects the idea of the greenhouse effect. We are going to look at learning objectives 6, 7 and 10 in this next section. Before I tell you all about the greenhouse effect, I'd like to just explain the 4 gases that cause the greenhouse effect. Here are the 4 gases. They are CH4, which is methane, water, carbon dioxide and nitrous oxide. These are the 4 gases that you should be concerned about with greenhouse gases. Every single one of these greenhouse gases has a natural source within the Earth. These gases are produced naturally. Methane is produced in the wetlands and the oceans and lakes. Water is produced by the evaporation from all water on Earth. Carbon dioxide is produced by volcanic eruptions and the evaporation of water. And nitrous oxide is caused by forests, soil and oceans. These are all natural sources. However, we, in the industrialization period, have included some man-made sources of these gases. The man-made sources of these gases of methane include farm animals, and I will let you go and read about how farm animals produce methane, but I'll give you a clue. It's a bit stinky and it comes out the opposite end of their mouth. Coal production and during burning of the biomasses, these man-made sources produce more methane than is naturally recognised in the Earth. Water, there are no man-made sources for water at the moment. The burning of fossil fuels in power plants and car exhausts cause an extra amount of carbon dioxide in the greenhouse gases. And finally, burning fossil fuels and deforestation cause a lot more nitrous oxide than we would expect through man-made sources. What these greenhouse gases do is they strongly absorb infrared radiation. Why is that a problem? Okay. Greenhouse gases have quantized electron levels, and you've seen this before in earlier parts of the topic. These electrons exist within energy states. If they receive energy, they'll jump up a state, and if they lose energy, they'll jump down a state. And the receiving of energy comes from photons of particular types of energy, and the losing of energy means a release of photons. Okay, well, these greenhouse gases have quantized electron states, and the infrared photons from the Earth, because remember I've told you the Earth radiates infrared radiation. These gases absorb these infrared photons, causing the electrons to jump up an energy level. but they're highly unstable, and they immediately transition back to a lower state, emitting an infrared photon. So they've taken in an infrared photon and they've released an infrared photon. The difference is that the photons that are released are emitted in all directions. So the photons that were previously leaving the Earth's surface are absorbed and then re-emitted in all directions, which means some photons of infrared radiation will be emitted back towards the Earth and will cause additional warming of the Earth's surface. I'm going to go back to this diagram here. The Earth emits infrared radiation because of Wien's displacement law. Some of the infrared radiation is absorbed and re-emitted by the greenhouse gas molecules. This infrared radiation was heading straight out of the Earth again, but the greenhouse gas has absorbed it and re-emitted it in all directions. So instead of all the radiation heading straight out, some of it is redirected in all directions back down towards the Earth's surface and heats up the Earth more. The energy level process of absorbing and then re-emitting infrared photons is not the only process or the mechanism that's happening within these greenhouse gases. Greenhouse gases are molecules which can be treated as a mass spring system. If you imagine H2O, where we have two hydrogen atoms and an oxygen atom joined by a spring, this system will have a natural frequency of oscillation which coincides with the frequency of infrared radiation. So the infrared radiation that's been emitted from the Earth's surface has a certain frequency, and that frequency is very similar to the natural frequency of this mass spring system. That means that the mass spring system will absorb the radiation and cause resonance. You can now imagine these molecules oscillating very quickly back and forth. This resonance causes the re-emission of photons in the infrared wavelengths in all directions. Again, the point I'm trying to make through is the infrared radiation from the Earth is absorbed by the greenhouse gases and then it's re-emitted in all directions. Here are what the examiners say about this. The physics of infrared absorption was poorly described. The underlying processes of resonance and vibrational energy states of the gas molecules were not widely appreciated. So do remember that greenhouse gases absorb and re-radiate infrared radiation in all directions using this process and this process. I think it's also important to clarify this idea of scattering. Some important facts. These are the important facts you've got to remember. The process of greenhouse gases absorbing and then re-emitting infrared photons is called scattering. They are not reflected at this stage. Please don't confuse the word reflection and scattering. The infrared photons are re-emitted in all directions, i.e. some back towards the Earth, and this causes more infrared photons to be absorbed by the Earth's surface and warm it up. The examiners are particularly worried about this concept. They have said confusing reflection or scattering with radiation was a common error in the explanations. Please don't make that error. At this stage up here, as the radiation reaches the greenhouse gases, it is reflected. At this process here, where the infrared radiation is absorbed and then re-emitted, it is scattered. Please understand the difference between the two. And then we can get back to those naughty examiners and say we understand. Okay, let's head to your revision note template, and I'm going to leave it up to you to note out that section. I suggest going to the other notes section and writing notes on how the scattering and reflection of the four greenhouse gases affects the greenhouse effect. If I were you, I'd go to common diagrams and I'd draw that mass spring system of the molecule and note out what's actually happening there in terms of absorption and re-emission. The greenhouse effect is a natural occurrence, and these four greenhouse gases are also naturally occurring, but humans are not helping it. Humans are burning fossil fuels, which enhances the greenhouse effect, and I'd like to look at that concept now. Previously, we talked about these greenhouse gases and we said that they were a natural occurrence. There are two types of greenhouse effect. One is natural and one is enhanced. The natural greenhouse gases mean that the greenhouse effect is a natural process. We need the natural greenhouse effect. Otherwise, the Earth would be 32 Kelvin colder. It would be an extremely cold place. We couldn't survive. However, the enhanced greenhouse gases and the enhanced greenhouse effect is due to the man-made gases which cause an additional warming, more than we naturally can cope with. And studies show that the levels of carbon dioxide in the Earth's atmosphere has increased significantly since the industrialisation period, where we started to produce energy using fossil fuels and transportation using petrol and diesel. So since we started driving cars, making energy from coal, we have put more greenhouse gases into the atmosphere, which is causing the Earth to heat up more than we originally had before, more than the natural effect causes. And our actual examiner feedback says that the descriptions of the enhanced greenhouse effect were generally poor, lacking in precision and relevant detail. Few candidates mentioned the random direction of the re-radiation by the greenhouse gases. This point is coming up again and again and again. Remember, the greenhouse gases emit radiation in all directions, and you're pretty much there. We come back to our killer concept now. Please, the ozone layer has nothing to do with the greenhouse effect for the purposes of the IB exam. The ozone layer is there to absorb UV radiation. It's to stop us getting sunburn. Yes, the ozone layer has been depleted. There are holes in the ozone layer because of nitrous oxide. But it doesn't contribute to the greenhouse effect. The greenhouse effect is something completely separate. Don't mention the ozone layer when you're talking about the greenhouse effect. And the examiners agree with me on this. A large number of candidates confused global warming with a depletion of the ozone layer. They have nothing to do with each other. Global warming is to do with the addition of extra greenhouse gases causing it to heat up more, whereas the ozone layer is to do with gaps in the ozone layer causing skin cancer and more sunburn because UV radiation can penetrate the atmosphere. You know what the greenhouse effect is, the natural one and the enhanced one, and you know why this enhanced greenhouse effect takes place. Can you go to your other notes section just now and write some notes on that? Then I highly recommend you head to the knowledge questions that are underneath this tutorial and work through all of them. I'm very aware that I didn't get you to do the questions as we went through this tutorial. That's because I feel like this topic should be done as a whole before the knowledge questions are attempted. Go and have fun. Bye.